Example, solve 3 to the power x equals 4. Well, in the other one we saw a way of writing that down straight away. This way we're going to look at it in a more kind of log style. Because we're trying to find the unknown, and the unknown is a power, what we're going to have to do is we're going to have to log both sides. So if we log both sides, we get log 3 to the x equals log 4. Using our log rules, I can bring that power down to the front, so I get x log 3 equals log 4. And just a little bit of algebra here, log 3 is just a number, so x equals log 4 divided by log 3. Don't get your rules confused, there's nothing more we can do with that, but it doesn't really matter what log base I use in any of this, which is why I've not written one in. Standard, if I don't have a log base, I'm assuming it's 10, but it could be anything. Log to the base a of 4 divided by log to the base a of 3. It works for everything. Another example, solve 5 to the power x plus 2 equals 101. Different ways I could do this. I could change that into 5 to the x times 5 squared and get rid of the 25 at this stage, but I'll just run with my logs at the moment. Trying to find a power, log both sides. Log of 5 to the x plus 2 equals log of 101. Bring the power down to the front. Remember, it's that entire thing. So I get x plus 2 log 5 equals log 101. Divide through by my log 5. X plus 2 equals log 101 divided by log 5. And now to get x on its own, I just minus the 2. So I get minus 2 plus log 101 over log 5. Solve log to the base 4 of x plus 3 minus log to the base 4 of x equals 3. Here I've got a log base in, but notice not all of the terms have got a log in them. So I'm going to have to do something clever. Best thing for me to do is to combine my logs. So a log minus a log is the same as log to the base 4 of x plus 3 over x, and that equals 3. Now I want to undo my log. If you remember when we first defined what a log is, it's all about the power. So log to the base 4 means that the x plus 3 over x equals 4 to the power whatever's on the other side. So in this case it's 4 to the power 3. 4 to the power 3 is 64, multiply through by the x plus 3 equals 64x. Get rid of the x, so I get 3 equals 63x. So x equals 3 over 63. So x equals 3 over 63, simplified to 1 over 21. Another example, if log to the base 2 of y equals 15, find log to the base 2 of 8y. Don't be tempted to work out what y is, there's no point, it's some stupidly big number. Log to the base 2 of 8y is the same as log to the base 2 of 8 plus log to the base 2 of y. Well, log to the base 2 of 8 is the same as log to the base 2 of 2 cubed. 8 is the same as 2 cubed, which is the same as 3. So I get that to equal 3 plus log to the base 2 of y, we get told was 15. 3 plus 15, 18. More involved example here. Solve 5 to the power 2x minus 6 lots of 5 to the power x equals 0. The trick that you really need to kind of know with this is that 5 to the power 2x is exactly the same as writing 5 to the power x squared. So in this case I'm going to write that as 5 to the power x squared minus 6 lots of 5 to the x equals 0. In this case you spot it's a quadratic straight away. Some people would like to use a substitution, say capital X. So capital X squared minus 6 lots of capital X. I'm just going to run with it. So I get 5 to the power x on the outside, factorising it, open brackets, 5 to the power x minus 6 equals 0. That gives me two solutions, 5 to the power x equals 0 or 5 to the power x equals 6. Well, the first one, 5 to the power x equals 0, doesn't happen. For an exponential graph, it never actually equals 0. It gets really close, but never equals 0. So that one has no solutions. 5 to the power x equals 6. I'm trying to find my power, so I'm going to log both sides. So I bring down the power. X log 5 equals log 6. X equals log 6 over log 5. Thank you.